Hi, I'm Major Derek Worth at the Air Force Institute of Technology, and in this video, I demonstrate relative vectoring using dual object detection for autonomous aerial refueling. Decades of ingenuity and innovation have resulted in aircraft that can refuel mid-flight, extending how far and long they can fly in a single sortie. Even more remarkable, unmanned aircraft can do the same, though at present only when a human is on board one of the two aircraft. Currently, aerial refueling requires the keen eye of a well-trained human pilot, someone who can guide the probe to the drogue from mere eyesight. A common attempt to automate this process without vision includes the use of differential GPS with IMU data. Unfortunately, satellite signals can be spoofed or jammed, and inertial sensors tend to drift over time. In contrast, computer vision uses imagery as shown here, which is impervious to spoofing, jamming, and drift. From this video, it is easy to imagine how a computer can estimate the location of the drogue in relation to the camera. Unfortunately, current solutions throughout the literature stop here and simply ask, where is the drogue relative to the camera? In our vision pipeline, we ask a slightly different question. Where is the drogue relative to the probe? Let me explain. With this image, current computer vision can find the location of the drogue relative to the camera. If we know the precise probe offset through extrinsic camera calibrations, we can easily compute the probe-to-drogue vector. However, what happens when the probe offset changes due to turbulence or some other effect? We lose our probe-to-drogue vector. Our proposed pipeline repositions the camera such that the computer vision can find both the location of the drogue and probe. From here, we can again easily compute the probe-to-drogue vector. This voids the need for extrinsic calibrations and dynamically adapts to changes in real-world situations. Our vision solution consists of 5 stages. First, we capture an image containing both the probe and drogue. Next, we use machine learning to find 2D points across the two objects within the image. We then match 2D image points with corresponding 3D object points, and use the perspective endpoint algorithm to transform the matches into pose estimates. Finally, we convert the object pose estimates into a relative probe-to-drogue vector rotated into the receiver's estimated local reference frame. Let's see how all this plays out in simulation. Our scenario includes a receiver aircraft flying multiple random approaches behind the tanker. As shown here, we mounted several virtual cameras on both the receiver and the tanker. In this effort, we report results from 3 of these vantage points, namely the receiver wing cam, dash cam, and tanker pod cam. The bottom right viewport displays the output of these cameras, which our pipeline uses for relative vectoring. Enlarging the viewport for just a moment, what you see highlighted here are yellow points our pipeline tries to find, overlaid with blue points it actually finds. These blue points are then transformed into probe-to-drogue vector predictions. To reveal what's happening under the hood, let's take a look at this diagram. In our pipeline, we trained YOLO version 5 with a novel supervised learning method to find specific 2D points. More on that in just a bit. But for now, let's focus on what our pipeline does with these points. Model point matching is fairly straightforward since YOLO also predicts class IDs. We pass these matches to perspective endpoint, which uses them to align our 3D models for pose estimation. The resulting pose estimates include a pair of rotation matrices and translation vectors defined relative to the camera. We subtract the camera frame probe vector from the camera frame drogue vector, which gives us a camera frame probe-to-drogue vector. We then rotate this vector into the receiver's local reference frame by multiplying it by the transpose of the probe's estimated rotation matrix. The end result is a receiver frame probe-to-drogue vector that an autonomous agent can use to navigate aerial refueling approaches. In this demonstration, we turn off YOLO predictions and replace them with true 2D image points. With 0 pixel error, the pipeline produces sub-millimeter pipeline accuracy, even when over 120 meters out. Adding random noise to these truth points clearly shows the negative effects pixel error has on probe-to-drogue vector predictions. Thus, we can conclude that accurate 2D image point detection is the most critical phase of the relative vectoring pipeline. We accomplished point detection in our pipeline using YOLO, a state-of-the-art object detector. However, the problem with using its traditional bounding box predictions is that the perceived 2D object center in the image is rarely the same as the true 3D object center projected into the image. This is due to what we refer to in this effort as the parallax effect, which is caused by the disparity in projective geometry between points closer to the camera's image plane and those further away. To visualize this effect, let's take a look at this two-dimensional square floating in three-dimensional space. When we form the tightest fitting bounding box around it, we see that the only time the true and perceived centers align are when the camera's image plane is parallel to that of the square. Any rotation of either the square or the camera causes the perceived and true centers to diverge. This effect gets even more complex with three-dimensional shapes. To overcome this effect, we propose bounding box corrections, such that we grow two adjacent sides of the tightest fitting 2D bounding box until its center aligns with the projection of the true 3D feature center. To automate this process within our pipeline, we define features by selecting 3D points across the surface of an object and use the geometric center of each corresponding point cloud as the 3D feature center. We then apply our bounding box corrections to the point clouds as shown here and save the bounding boxes with their corresponding image to file. This automated process allows us to generate approximately 30,000 precise, error-free labeled images an hour. In addition to bounding box corrections, we augment approaches with various backgrounds, lighting effects, orientations, and occlusions. This, paired with default YOLO v5 augmentations, ultimately leads to better generalization and model performance. After training our models from labeled images with bounding box corrections applied, we observed YOLO was able to find 2D image points with enough precision to produce highly accurate probe-to-drogue vectors. Here, we also demonstrate our pipeline does not rely on extrinsic camera calibrations. Shifts in camera position and orientation do not affect pipeline predictions. To quantitatively assess pipeline performance, we collected millions of observations across tens of thousands of random approaches in Monte Carlo simulation, comparing truth to pipeline predictions. We found that by switching between multiple models specifically trained on different phases of the approach, the pipeline was capable of navigating the receiver's probe to the drogue with high accuracy, reliability, and speed from 120 meters out. Overall, results show our relative vectoring pipeline is resilient to occlusions, does not require any extrinsic camera calibrations, is reliable and consistently accurate to within 3 centimeters at contact, and runs at least 45.5 frames per second, making it suitable for autonomous aerial refueling. Thank you for watching, and a special thanks to our sponsors at the Naval Air Systems Command and Air Force Aerospace Systems Directorate. This research was possible through your continued partnership and support.